Welcome back to McArdle Math Academy, everybody. In this video, we will be talking about independent events, and we will be looking at a specific application. Before we look at an example, let me remind you of the definition. We say that two events, E and F, are independent if the conditional probability of E occurring, given that F has occurred, is just the probability of E. And what this really means is that the occurrence of F has no effect on the probability of E. And the same goes for F. The probability that F occurs given E, this is your conditional probability notation here, is just the probability of F. So the condition of E occurring has no effect on the probability of F. And you can use your logic here and just think E and F are essentially unrelated events. The beautiful thing is that if we have two independent events, then we can find the probability of the intersection, or the probability that both E and F occur, and it's simply the product of the probability that E occurs with the probability that F occurs. So let's look at the following example. On any morning, the probability that Eli eats breakfast is about 80%. All right, and suppose we know that the probability that Allie eats breakfast is about 30%. And the question is, what's the probability that exactly one of them eats breakfast? So let's let E be the event that Eli eats breakfast, and F be the event that Allie eats breakfast. And to solve this problem, I'm going to show you two different methods to approach it. And so method one, what we're first going to do is we're going to look for the probability that both Allie and Eli eat breakfast. And because these events are definitely independent, I can use the formula that we saw on the previous slide. So I have that the probability that Eli eats breakfast is 0.8, and then I multiply that by the probability that Allie eats breakfast, which is 0.3. So we have 0.24. Now once we have this information, we can actually put it all onto a Venn diagram, which I'm going to do here. So I have a Venn diagram with the events E and F, and I've placed 0.24 in the center where that's the event that they both eat breakfast. Now I can fill in the rest of the Venn diagram here using the fact that P of E is 0.8. I know that the entire E circle must be 0.8, so that leaves 0.56 to be out in this region, and 0.06 to be in this region here, because the probability of Allie eating breakfast is 0.3 total, and 0.24 is her eating it as well as Eli, so we have 0.06 left on the outside. So now I can answer the question pretty easily, because if you recall, I was asked what the probability that exactly one of them eats breakfast. What's the probability that exactly one of them eats breakfast? Well, notice that I have a 0.56 probability that it's only Eli eating breakfast, and I have a 0.06 probability that it's only Allie eating breakfast. So to find the probability that exactly one of them eats breakfast, I need to add the probability that only Eli eats breakfast to the probability that only Allie eats breakfast. And we have our final answer that exactly 62% of the time, or with a probability of 0.62, exactly one of Eli or Allie will eat breakfast. Now there's a second method that can be used to solve a problem like this, and that involves a probability tree. So what I'm going to do is pretend like I'm the one observing whether Eli and Allie ate breakfast or not. So I first go to Eli, and either Eli ate breakfast or Eli did not eat breakfast. And I can add probabilities to this probability tree as well. Then I can proceed in each situation to go and observe whether Allie ate breakfast or not, and add probability to those branches as well. And again, I'm getting these probabilities just from the statement of the problem. So Eli eats 80% of the time, does not eat 20% of the time, and Allie eats 30% and does not eat 70%. So the way this tree is interpreted is, if Eli eats and then I go and observe, I can see that Allie eats or Allie does not eat. If Eli does not eat breakfast, then either Allie eats or Allie does not eat. And the question says, how often does exactly one of them eat? So I take my highlighter and I go through and I say, okay, so I could either go up and have Eli eat, but then I need to force Allie not to eat in order for this to be satisfied. Or I could go down and have Eli not eat and force Allie to eat as well. So those two branches are the ones that are described by the question that we're trying to answer. How often does exactly one of them eat? So what we have to do is sum those branches, sum the probabilities from those branches. So let me move this over here. And our first branch is 0.8 times 0.7, and the second branch is 0.2 times 0.3. And our final answer is 0.62, as it was with the previous method. All right, I hope this example helps, guys. I'll see you next time.